Hello, my name is Brandon Wers, and this is a brief look into how definite integrals in mathematics can be used to calculate the area of a given space. Now, first of all, we're going to need to go into what definite integrals are and what they can be used for. So a definite integral, as defined by the text Calculus Volume 1 by the group OpenStax, is defined as generalizing the concept of the area under a curve, quote. And to be more precise about this a definite integral is the series of y values of a function within specified bounds. It is a sum of all the y values and their distance from the x-axis of a given function, and that can be seen represented by this definition of an integral by what's called a Riemann sum. And so essentially what this is saying is that if you were to take a function, some kind of curve on a graph, and define it, say, as a rectangle, and get it more and more precise by lessening the number of rectangles, shortening the width of each one, and matching those rectangles up with the curve itself. And you kept going until you had an infinite number of rectangles. You could use that to calculate the area of between the curve and the x-axis. To go over a simplified history of how this came to be as a mathematical concept, part of this technically originated with ancient Greek mathematics and how mathematicians of the time used what is called the method of exhaustion in order to approximate the area of a shape using a sequence of polygons. Without going too deep into it, essentially they would take a polygon and approximate it to the area of another one and exhaust whether it was less than the area of the given shape and then more than, and when both of these are proven false and exhausted, they would prove by contradiction how to determine the area of the shape. And they did this and determined the relation between the difference of the area of the two shapes without having actually discovered the modern concept of limits in modern calculus. Later in the late 17th century, several mathematicians who are commonly known as the founders of calculus, to say Newton, Fermat, and Leibniz, would develop this concept into what is called integration and established its link to differentiation. And they determined that when integrating something, you are effectively using what is the antiderivative to the derivative that differentiation would take. And they established this relationship between the two, and they also established the application of integration in order to determine the area under a curve. And so that is what brings us to the application of using definite integrals, that is to say, an integral that has its bounds defined instead of being across the whole function. They can be used to determine the area under a curve. And as said before, this is the distance that the function is from the x-axis at all given points within the specified bounds. And this has significant real-world applications in that you can take a given shape and define its shape as a function or several functions if need be, and determine the area within that curve and use that to determine the area of the original shape. And so for a given example, let's say that this perhaps is something that's involved in a construction project or an architecture where we need to determine how much material to fill this given space with, and so we need the area of this space, and we define it, the upper part of this surface, as the function f of x equals cosine x plus 3 with a length of 4 pi inches. And how we go about this is, first we format the function as an integral, as a definite integral to be specific. And so this is from 0 to 4 pi, the function cosine x plus 3 times dx in relation to x. And next, the antiderivative of the function is determined. In this sense, we are effectively finding the original, we are effectively finding the, how to say it, the function that would result in the original being its rate of change. And for example, if you were to take the function 3x and you were to observe how much it's changing, what its slope is over time, you would determine that it is 3. It is changing by 3 units, going up 3 units every step. And so for that, its derivative would be 3. And so the antiderivative is the reverse of this, where we assume the original function is a rate of change, and we find what function would have that rate of change. And so in applying that process, we find that cosine x becomes sine x, 3 becomes 3x, and then we add also a plus c, which technically isn't necessary in this specific application, but it is added for demonstrative purposes. And it effectively represents that when calculating an antiderivative, there could be any number of constants added on to the end, and they would all cancel out when deriving the function. So the plus c is added to clarify that there is an unknown constant that could be taken into account with this antiderivative. And so on the right, this is still being taken from the bounds of 0 to 4 pi. And so using the fundamental theorem of calculus, what we do is we substitute x for 4 pi and then subtract that for the same function with x substituted for 0. And this is taking the area and subtracting its lower bound of this function. So when calculating sine of 4 pi, that just becomes 0. 3 times 4 pi becomes 12, plus c is unaffected. And then on the right, sine of 0 is 0. 3 times 0 is 0, and c is just affected by the negative. I just saw a mistake in the thing that the second 0, well, the third 0, should have a minus sign, but it's inconsequential as 0 is not positive or negative. And so the c's cancel out, hence why it's ultimately inconsequential in this application of definite integrals for antiderivatives. But the last remaining term is 12 pi, and so it is determined that the area of the space is 12 pi inches squared. And there are many different real-world applications in which this can be applied. For example, if you were to be building a swimming pool and it had an unusual contour, like it was not particularly a rectangular prism, then let's say it was curved at the end for if you wanted to create a deep end or have the shape of the pool be an ellipsis to have a more like circular pool. You could use definite integrals to represent these ideas as functions and as curves and determine the area under them in order to calculate this. And then this also applies to, as shown in the previous example, in construction and architecture. These are the sources that I used for this brief look into definite integrals and their application for area. I used the text Calculus Volume 1 with OpenStax to research definite integrals. I used the Encyclopedia of Mathematics and its pages to research the origins of integral calculus. And I used Desmos for graphing images and Overleaf for mathematic expression images.